Okay, for what we have moving along with eigenvalues and eigenvectors, we have this time around the diagonalization of matrices, and we have with the following theorems. Here we have first of all a square or n by n matrix A is diagonalizable if and only if A has n number of linearly independent eigenvectors. In fact, A is equal to P times D times the inverse of P, where D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in P. And for this part, we will be looking at the determination of P as well as the entries for the diagonal matrix D. And we have also added n, and n by n matrix with n number of distinct eigenvalues is diagonalizable. All right, and we have in the case of diagonalization, okay, we have first of all we have a 2 by 2 matrix, and we have it says to diagonalize the following matrices if possible. So we have in the lineup, okay, we have with the first matrix, okay, we have a 2 by 2 formation. First column we have at 3 and 1. Second column we have at -1 and 5. And going back to the setup for the characteristic equation, initiating, we have taking the difference between A and lambda I. Okay, so we have again, so you have 3 minus lambda, -1, 1, 5 minus lambda, and we have in the case of the determinant of this difference, okay, so we have the quantity 3 minus lambda times that of 5 minus lambda minus the diagonal product of negative and positive 1 set equal to 0. And from this, okay, we have a square trinomial, okay, whereupon we have in this case we have lambda squared minus 8 lambda plus 16 is equal to 0, and there's only one eigenvalue from this, whereupon we have that lambda is equal to 4. And so what we have in the case of what we have for lambda equal to 4 for a minus lambda I, we have equal to a minus 4I. And looking at what we have here, so you have 3, 1, -1, 5 from A, and minus 4I, we have the subtraction of 4, 0, 0, 4. And for the difference, for the corresponding parts, okay, we have, again, going column by column, we have -1 and 1, and again, -1 and 1. And just going back to the quantity of A minus lambda I times X is equal to 0, okay, and this time we have A minus 4I quantity times X equal to 0. We have with our augmented matrix, okay, so you have -1, -1, 0 for the top row, 1, 1, 0 for the bottom, and reducing, okay, and placing in reduced echelon form. Okay, so we have 1, 1, 0, and then we have 0, 0, and 0. And the bottom row signifies that x of 2 is going to be a free variable, whereas in the case of x of 1, we have x of 1 plus x of 2 is equal to 0. So you have x of 1 is going to be equal to negative x of 2. Again, x of 2 is free. And for the eigenvector that corresponds, okay, we have with the solution, we have x equal to x of 2 times the vector -1, 1. And again, a basis for lambda equal to 4. Again, we have the only eigenvector there is, and that's going to be at -1, 1. And from this, okay, in trying to find out if we can diagonalize, okay, and I'm just looking at this from an eigenvector perspective. There is only one linearly independent eigenvector, while A has 2 rows and columns. And so since there's a deficiency with the number of eigenvectors that are linearly independent, A is not diagonalizable. All right, now if we look into next case, all right, so we have the A is at 2, 10, 2, 3, and for the difference between A and lambda I, again, we have 2 minus lambda, 10, and we've got 2 and 3 minus lambda. And in looking at the determinant of A minus lambda I, for what we have in this formation. So again, taking the difference between the diagonal products, okay, we have with our characteristic equation, okay, this will become lambda squared minus 5 lambda minus 14 is equal to 0, and we have the quantity of lambda plus 2 times that of lambda minus 7 equal to 0. So either case, okay, have the characteristic equation from which we have to emanate the eigenvalues -2 and 7. All right, so we have two distinct eigenvalues, and looking for the eigenvectors. Okay, so for lambda equal to -2, okay, we have a minus lambda I is going to be equal to a minus -2i, which would be a plus 2i. So for a plus 2i, okay, we come out to 410, 2, 5. And for a minus lambda I quantity times x, again, this will be the quantity of a plus 2i times x is equal to 0, and putting in reduced echelon form. Okay, it turns out that x of 2 is going to be a free variable, and we have x of 1 is equal to -1/2. So we have that x is equal to x of 2 times the matrix or the vector -1/2 and 1. And we have a basis, not necessarily the lone basis, but a basis for lambda is equal to -2 is going to be the first eigenvector set equal to -1/2 and 1. As for the other eigenvalue at 7, okay, so if I run it through the mill like a minus lambda I with lambda at 7, we have the difference at -510 to -4 if we go column by column. And for the lead-in, we have for a minus lambda I quantity times x, in this case with lambda at 7 and setting to 0, we have with the augmented matrix. Okay, so I have -520, 10, -40, and just running through the process, and we have with the reduced echelon form. Okay, so I have 1, -2/5, 0, and 0 is at the bottom. So again, x of 2 is going to be a free variable, and x of 1 is equal to 2/5 of x of 2. And we have for the solution in x, again, you have x of 2 times 2/5 of 1. And we have as a basis for lambda equal to 7, again, we have the eigenvector, which we will label as v of 2 is equal to 2/5 and 1. Now, again, I said we will be looking at the determination of P, or a determination of P, as well as the diagonal. So we have for P, okay, we have just for P, we have again the augmented matrix where we have containing the eigenvectors. So for P in this case, all right, we have with both bases, we have -1/2, 1, which again we had to correspond to the eigenvalue lambda equal to -2. And we have for the second column, we have 2/5 and 1, which was the eigenvector corresponding to the eigenvalue at 7. And so we have for the diagonal D, okay, so if I put this in the 2x2 formation, so the so just corresponding with the first eigenvector, okay, we have the upper left hand section, so we have -2, and we have with the second eigenvector we had lambda equal to 7, okay. And now the author says that it doesn't matter what order you place this, but just to maintain consistency, I like to just put, map together the first eigenvalues and eigenvectors together. Okay, so you have for the diagonal, so you have -2, 0, and 0, 7. And just to mention, you can check by verifying that the product of A and P and the product of P and D will be the same value. So just kind of run and get through the process. So for A times P, you have A times P, and just like AP1, AP2, and melding together. Okay, so you have 1, -2, 14/5 and 7. And for P times D, okay, so you have your P, and the D is the diagonal, and just running it together, PD1, we have 1, -2, PD2, we have 14/5 and 7, putting together, and notice that the products are the same. So this particular matrix A is diagonalizable, where again the diagonal would come out to -2, 0, 0, and 7.